Hello, my name is Keith Corso, and I'm with ABATRON, a manufacturer of building and restoration products. I will be your point of contact for any follow-up questions. Today's presentation is on the subject of sustainable design using epoxies in the restoration of wood. Our presentation will be based on this outline. After a brief introduction, we will define our 4 course learning objectives. These objectives are wood restoration contributions to sustainable design concepts, physical properties of wood and causes of deterioration, physical properties of epoxies, applications and uses of wood restoration products. This will be followed by our conclusions. To introduce you to the subject matter, we will focus this presentation on epoxies and their applications in the repair of wood. Epoxies are a mixture of resins and hardeners with strong adhesion and bonding capabilities. They are extensively used in building restoration and historic preservation. Examples that we will be giving you focus on the restoration of natural wood building components instead of man-made wood products. Our company is registered as an AIA-approved provider of this course. This course will be 1 hour long, followed by a 10-question quiz at the end. Upon successful completion, you will satisfy the requirements for 1 learning unit in a sustainable design topic. We will certify the results with AIA and send you a certificate of completion. At the end of this course, you will understand that wood repair is an option to achieve sustainable design goals. You will also have a better understanding of the physical properties of wood and the causes of wood deterioration. You should have a clear understanding of the physical properties of epoxy compounds used in wood repair and how they are applied to wood. Here is an illustration of the many typical uses and opportunities of epoxy compounds for wood repair in a typical large, older building. These uses include, but are not limited to, windows, rafters, balustrades, now on a smaller scale, such as an older home, there are additional opportunities of epoxy compounds for wood repair, such as columns, handrails, corner posts, clapboards, doors, decorative brackets, and fascia boards. As our first course objective, we are establishing that wood restoration using epoxies is a reasonable option to achieve and address sustainable design goals. Epoxies are addressed in the Committee on the Environment's Measures and Metrics, and epoxies are also addressed in the AIA 50 strategies adopted toward a 50% reduction in carbon emissions. Epoxies are relevant in sustainable design because they can be non-toxic, they can last indefinitely, and they can strengthen existing wood products and structures. Epoxies can improve material performance and lengthen the lifespan of wood structures. Reusing wood instead of disposing it reduces scrap and disposal costs and saves landfill space. There are cost savings when restoring wood in comparison to replacing wood. It is estimated that labor costs to restore and paint a wood window are 60 to 70% less than the cost of replacing and painting a wood window. The AIA has a Committee on the Environments. This committee has 10 subject areas of high importance in attaining sustainable design goals. The subject that we will be focused on is the area of materials and construction. Epoxies address materials and construction in three ways. First, epoxy used in wood products reduces product cycle environmental impacts by extending the lifespan of wood components. For example, a 40-year-old wood-framed window with minor decay deterioration may last an additional 40 years or indefinitely with proper maintenance. This holds true when the source of decay is halted and the decayed voids are filled with an epoxy and repainted. Second, epoxies improve the performance of existing wood products by strengthening them where they have deteriorated. In decayed wood, strength vanishes, but is restored when the wood is replaced with an epoxy wood filler, used in conjunction with an epoxy consolidant. Third, epoxy repairs to windows and doors return the components to like-new condition, eliminating building heat loss and improving the overall comfort of building occupants. The AIA has 50 strategies to reduce carbon emissions by 50%. Two of these strategies are to preserve and reuse existing building facilities and encourage the repair of windows and openings. Many examples of what you will be seeing in this presentation involve the restoration and repair of windows and other openings. Here's an example of an epoxy repair on a window. In the first panel, a consolidant is applied to decayed wood. In the second panel, an epoxy filler is added to fill a decayed void, and in the third panel, we see the finished and painted window. Here is an example of a restored wood church window prior to painting. Here are some additional examples of where epoxies have been used to preserve government buildings. As our second course objective, I will focus on the physical properties of wood and the causes of deterioration. I will discuss wood uses, properties of wood, moisture in wood, wood strength, wood decay, and wood preservatives called borates. Wood is a natural product and a renewable resource. Typical uses in a building include structural timber, light framing, siding, exterior finishes, windows, trim work, doors, frames, sheathing, roofing, subflooring, flooring, building carvings, turnings, and statuary. To understand the beneficial relationship between epoxies and wood, we must first understand the properties of wood. Wood is a porous product made up of long, hollow cells of cellulose packed together in a parallel configuration. This is similar to minute straws being packed together. Wood is a flexible product where water moves in and out of wood as it expands and contracts or shrinks. Moisture content is measured in terms of percentage of water weight to total weight. Green lumber has a moisture content that ranges from 30 to 90%. Once it is processed, the moisture content is reduced to a range of 8 to 12%. Until coated, water moves freely into and out of wood. Wood strength varies by species. Flexural strength, or wood's ability to bend, can range from 930 to 1,990 pounds per square inch, or PSI. Compressive strength, which is wood's resistance to compressive forces, can range from 870 to 7,400 PSI. It should be noted that compressive strength of dry wood is 1.5 to 2.5 times higher than saturated wood. This is another good reason to keep wood dry. Shear strength, which is the wood's resistance to tangential forces, can range from 700 to 1800 psi. Tensile strength, which is the resistance of pulling forces, ranges from 175 to 1800 psi. Here is a diagrammatic illustration of simple forces acting on wood to illustrate wood strength. Now we need to understand how wood deteriorates so that we can stop the deterioration and correct the process. Although there are many causes of wood deterioration, the most common is decay feeding on moist wood. Other forms of wood deterioration are caused by ultraviolet light, split grain, broken parts, end checks, nail holes, knot holes, absorbent end grain, and insect infestations feeding on moist wood. All of these forms of deterioration have one thing in common. They permit unwanted moisture to enter the wood. Even though moisture content in newly processed wood ranges from 8 to 12%, additional moisture enters the wood through minor damage and coating failures. When moisture content exceeds 20%, it becomes excessive and is subject to decay. Excessively moist wood stimulates the growth of decay fungus, whereas dry wood inactivates the growth of decay fungus. It should be noted that inactive decay fungus is not dead, but only dormant. When wood becomes excessively moist, it becomes attractive to decay fungus and insects as a food source. Wood decay fungus is made up of spores that germinate into organisms that consume wood cells. After the fungus consumes the wood, the remaining material is called rot. This appears as a brown material. The brown material that is left is called lignin. Lignin is a complex chemical compound contained in all wood and is one of the few materials not consumed by the fungus. Here is an illustration of how the wood decay process progresses. A few of the typical causes of rot are paint failures, leaking roofs, bad flashings, excessive condensation accumulations, and snow accumulations. Here is an example of some rotted wood before, during, and after an epoxy repair. In the first slide on the left, a bay window was in place that could not be removed, and the surrounding wood material would not hold paint. So an in-place repair was necessary. In the center slide, the wood was treated with a preservative and dried. This was followed by the application of an epoxy consolidant and epoxy filler. The final slide on the right is the completed repair. Note that the repair is invisible. Here's another example of some rotted wood in a column before, during, and after an epoxy repair. Again, on the left, the base of the column has rotted away. On the center slide, a repair has been made with the application of an epoxy consolidant and an epoxy filler. It was then machined and sanded back to the original contour. In the last slide on the right, the restoration is completed and the repair is invisible. There are two types of rot that are found in North America. The first is called brown rot. In brown rot, up to 75% of the wood material is lost through the decay process. The material that remains is brown lignin that is cubic in shape. This is also sometimes referred to as brown cubic rot. The second type of rot is called white rot. In white rot, up to 95% of the wood material is lost in the decay process. This is because in white rot, even the lignin is consumed, and what remains is a material that is white in color and fibrous in shape. Here are some examples of where both white rot and brown rot are visible in a deteriorated beam on a building preservation project at Fort Totten in New York City. To treat wood rot, you must first dry the wood to inactivate the decay growth. The decay is then treated with a preservative containing a borate. To completely kill existing decay fungi, or insects for that matter, the preservative must be given 48 to 72 hours to penetrate the wood and dry. Before beginning the repair of wood with an epoxy, the moisture should be less than 20%. I would like to briefly describe what a borate preservative is. A borate preservative is a solution containing a dissolved borate salt. A borate is a diffusible wood preservative, which means that in solution form it easily spreads through a wood cell structure. The main ingredient is boron, a naturally occurring mineral salt. Chemically, a borate salt is called disodium octaborate tetrahydrate. This salt is mixed with water and applied to wood. Occasionally, borate salts are mixed with glycol for deeper penetration into the wood. Borates work because they are lethal to wood-eating insects and fungi only. Borates are marketed as wood preservatives, not pesticides. When insects and fungi ingest wood laden with borate, they are slowly poisoned through their digestive process, which occurs within 48 to 72 hours. Borate solutions are odorless, colorless, have low volatility, and are not corrosive to most metals. They are not carcinogenic and are not toxic to humans or other mammals, such as pets. As our third course objective, we will discuss the physical properties of epoxies and how they differ from solvent-based wood fillers. We will talk about the definition of an epoxy, the manufacture of epoxies and GREENGUARD certification, epoxies on a microscopic level, temperature ramifications, the characteristics of epoxies, epoxy modifications, solvent-borne polyesters, cement acrylic latex polymers. An epoxy is a thermosetting resin capable of forming tight cross-linked polymer structures characterized by toughness, strong adhesion, and low shrinkage. Epoxies are made up of two components, a resin and a hardener. When the resin and the hardener are mixed, a chemical reaction takes place and they harden into a solid mass. Epoxies used in wood seldom contain solvents or water. As a result, there is virtually no shrinkage. Formulated epoxies require minimal energy to manufacture. There are no byproducts or waste in the manufacturing process. Some epoxies are GREENGUARD certified. For those of you who are unfamiliar with GREENGUARD certification, let me clarify the meaning. GREENGUARD certifications are performed by the GREENGUARD Environmental Institute, an unbiased third-party organization. The certification gives credence to manufacturers' sustainability claims, backing them with scientific data and independent testing. The certification gives assurance that products designed for use in home, commercial, office, and other indoor environments meet strict chemical emission limits, thus contributing to the creation of healthier interiors. Let us discuss how an epoxy is created on a microscopic level. Single molecules, called monomers of the resin and hardener, combine. Chains of molecules are formed, called polymers. Hardening of an epoxy is the result of a reaction between the resin and the hardener. After the epoxy hardens, it then cures. Here is an illustration of how the epoxy molecule forms. There are temperature ramifications when using epoxies that you should be aware of. The chemical reaction between the resin and the hardener is called an exothermic reaction. This means that it generates heat. Adding heat speeds up the reaction, and reducing heat slows the reaction. Ideally, the temperature range when mixing and applying epoxy should be 60 degrees Fahrenheit to 90 degrees Fahrenheit. Epoxy components have a tendency to crystallize, which means that they get cloudy or go to a solid state when stored in cold temperatures. This can also occur to epoxies that have been stored a year beyond the date of manufacture. Although the components cannot be used when in this crystallized state, the components are not damaged, and crystallization can be reversed if the components have no solvents or water in them. However, the reversal process can be challenging if crystallization has gone to the point of solidifying. Shelf lives of unused epoxy components are typically limited to 1 year or longer by most epoxy manufacturers. This is due to the potential for crystallization. Epoxy manufacturers should be contacted whenever the user questions the quality of material being used, based on the previously mentioned indicators. Cured epoxies have great construction characteristics that complement wood building components. They have strong adhesion to most surfaces. The hardness of a cured epoxy can be varied by formulation. The density and flexibility of the epoxy material can be varied by design to match that of the wood. Cured epoxies are water resistant, bioresistant, and hold paint and coatings well. The curing process of a mixed epoxy is not reversible, and there are very few chemicals that adversely react with cured epoxies. Epoxies can accept pigments to change the color of the material or the consistency of the material. Also, varying the mixing ratios of resin and hardener can adjust the strength and hardness characteristics. Now, I would like to talk about wood fillers. All wood fillers contain an inert additive to give them a paste or putty-like consistency, but the similarities end there. There are differences that the user should understand. Other wood fillers on the market may contain polyesters or cement acrylic latex polymers. Although epoxy wood fillers, polyester wood fillers, and cement acrylic latex polymers all serve a similar purpose, they have very different strength and shrinkage characteristics. First of all, the bond strengths of polyester and cement acrylic latex polymer fillers are much less than epoxy fillers. Although the bond strength of a polyester or a cement acrylic latex polymer filler may be enough to hold the filler in place for the short term, keep in mind from our earlier discussions that wood is a material that shrinks and expands as moisture moves in and out of wood. If the bond fails, then cracking and eventual premature failure can occur. Secondly, the polyester and cement acrylic latex polymer fillers contain solvents or water as an ingredient. As the solvents and water evaporate, the results are a higher level of shrinkage. Epoxy wood fillers typically do not contain solvents or water and don't shrink. Finally, both the polyester filler and the cement acrylic latex polymer emit objectionable odors as they cure, creating problems for the users. This means that additional ventilation procedures will be necessary. As our fourth and final course objective, we will be discussing the applications and uses of wood repair products. We will be discussing the following: the consolidation method, the decay removal method, the DUTCHMAN method, working conditions, limitations of use, basic guidelines on use, comparing different epoxies, and epoxy specifications. The first method of wood repair that I would like to discuss is the consolidation method. In this illustration, you can see what type of deterioration has occurred and how the repair progresses. The first step is to stabilize the decay process by applying a wood preservative and allowing the work area to adequately dry out. Small holes may be drilled around the decayed area to maximize the penetration of the preservative and the eventual application of the consolidant. The next step is to apply an epoxy consolidant to the decayed area to consolidate and harden the wood decay in place. The epoxy will also penetrate the end grain of the wood and through drilled holes across the end grain. The next method of wood repair is called the decay removal method. Again, the illustration shows the extent of damage where this method is most advantageous. This method is best used when voids in the wood require an epoxy wood filler. As before, the decay must be stabilized first, as was done in the consolidation method. Then, instead of leaving the decayed material in place, excess decayed material is removed as thoroughly as possible. The next step is to apply a liquid epoxy consolidant. This is immediately followed by filling the voids with an epoxy wood filler of similar type. The consolidant acts as a primer and improves the bond between the wood and the epoxy wood filler. Once the wood putty has hardened, standard carpentry tools are used to bring the wood back to the intended contour. Now I'm going to demonstrate the application of an epoxy to a rotted piece of wood, such as you might encounter here. Note the decayed portion of the wood. I will start by mixing a epoxy hardener with an epoxy resin. Now let's get started. We will be mixing equal parts of resin and hardener together. This will be followed by a thorough mixing. We have mixed the two-part epoxies into one for approximately 2 minutes. We've also placed some of the mixed epoxy into a squirt bottle for applications into tight spaces. Now we will apply it to this piece of rotted wood. So we will thoroughly saturate the wood using both methods, with a brush and with a squirt bottle. We have drilled some holes around the decayed area to make it easier to saturate the wood with a squirt bottle. The epoxy will absorb into the wood, and multiple applications are advised. Now that I've finished applying the consolidant to the wood, I'm going to take the resin and the hardener and mix the two together. The mixture is now a common color. I will apply this mixture into the void. The void has now been filled. After it cures, which will take approximately 8 hours, you can machine it down to the original contour with carpentry tools or with sandpaper. The next method that we will discuss is the DUTCHMAN method. Again, the area of decay must be removed to the best of the user's ability, and the decay should be stabilized with a wood preservative and allowed to dry. At this point, a section of wood is cut and shaped to reasonably fit in the void created by the decay. This piece of wood is called the DUTCHMAN. The grain orientation of the DUTCHMAN should be parallel to that of the original wood to prevent warping. The section of wood should then be glued into the void with an epoxy glue. Remaining voids or gaps are then filled with epoxy consolidants and epoxy wood fillers. The final step is to work the composite back to the original contour after the epoxies have cured with the aid of standard carpentry tools. Dry conditions are best for working with epoxy fillers. This minimizes the possibility of decay fungus spores re-entering treated wood. It is also important to maintain dry conditions in the event of trapped decay fungus reactivating prior to painting or coating the wood. There are limitations in the use of epoxies. First, if solvents are an active ingredient in epoxies, then ventilation will be required. Secondly, some epoxies do not sand well or machine well after curing. Third, UV resistance of wood is not addressed until after the repair is painted. Finally, care should be taken if the epoxy is to be used for structural purposes and structural loads are involved. Consultation with a structural engineer is advised in these situations. All epoxy configurations are different due to proprietary formulations. When comparing various epoxies, the specifier should be looking at the following characteristics when choosing a material. First, look at the appearance of each component. If it is cloudy, then crystallization may be starting and require heating or reprocessing. Secondly, look at the color of each component and the color of the mixed components. See if the pigments can be added to change the color if this is important to the overall repair. An example is the repair of furniture. Thirdly, check the components and mixtures for odors as a sign of solvent additions. A solvent odor would indicate that the material is not GREENGUARD certified. Check the recommended mix ratios of the components. Does the manufacturer allow for the adjustment of the mix ratios? Compare the working times of the products as this will impact the labor costs. Compare the hardness of the cured material as this may indicate the ease of finishing with carpentry tools. Strength comparisons of epoxies are also important. An epoxy should have strength characteristics that reasonably match wood, or failure of the wood and epoxy composite could occur. Compare each proposed material on the basis of tensile strength, flexural strength, compressive strength, elongation, modulus of elasticity, shrinkage, flammability, carcinogenicity, and sag resistance. When preparing specifications for wood repairs using epoxy materials, care should be given. Specify ASTM standards to compare performance characteristics of the materials. When specifying warranties, it should be noted that manufacturers will only cover defects in manufacturing, not in the application. It is better to define or require a lack of shrinkage, strength and hardness levels, GREENGUARD certifications, require a mock-up to demonstrate the contractor's skill level, and the quantity and location of work involved. ASTM specifications are excellent references that should be included in your specification. Reference the following ASTM specifications in evaluating epoxies. ASTM D2393 regarding viscosity, ASTM D2240 regarding hardness, ASTM D638 regarding tensile strength, ASTM D790 regarding flexural strength, ASTM D695 regarding compressive strength, ASTM D638 regarding elongation at the break. There are sample specifications available in current CSI format for you to use in the projects using epoxies that are available at the end of this program. Please contact us if you would like a copy in digital format. In conclusion, wood repair with epoxies meets the Secretary of the Interior's guidelines for historic preservation. Epoxy repairs should be considered on older and historic buildings as a means of achieving sustainable design. To receive learning credit, please download a quiz at our website, www.abatron.com. Thank you for your time.